Hello, differential equation students. Topic 17 is an interesting topic. It's free harmonic motion, an application of differential equations. Now, suppose a string hangs from a fixture. A mass is attached to the spring, stretching it to a new length, obtaining a spring mass equilibrium. If this weight is displaced, then harmonic motion will ensue. Now, I'm going to cut over to Desmos and show you what I mean by this. So we have a mass dangling from a string, from a ceiling, we'll say. That black horizontal line is a ceiling, and that dot is a mass. And if that mass gets displaced, then we're going to see harmonic motion. It looks something like this. And in this case, we see that the amplitude of the harmonic motion is diminishing over time. We call this damped harmonic motion. But what we're going to be learning is how to create the differential equations and then solve those differential equations that model such harmonic motion. Let's cut back over now to our notes and pick up reading right here. The total force on the object is the sum of all the potential forces acting on that object and is given in the equation below, producing a second order ODE. So the total force, there's going to be four components. There's going to be the force of gravity acting on the object. There's going to be the spring resistance force. So if, for example, if the spring has a certain length and you compress it, then there's going to be a force pushing back this way. Or if you stretch it, oops, erase, that's what I want to do. If you stretch the spring, then there's going to be a force trying to pull it up this way. So we definitely need a frame of reference here to say what a positive direction is. And let's say that x equals 0 will be this length right here. And we'll say up is positive. So if I were to put the mass up here, and that was, say, 2 meters away from x equals 0, then that would be at position x equals 2. But if I put the mass down here, 2 meters below, then we would say that we're at x equals negative 2. Now, when we attach the mass to this spring and then let it stretch to a new length, this new length is this new position where this is at rest is called our spring mass equilibrium. And we want to call this one y is equal to 0. Ultimately, we're going to get everything in terms of y. So everything's going to oscillate around y equals 0. It's going to be doing, your motion will be something like this. And up will still be positive, and down will be negative. Okay, so we have the resistance, the spring resistance force. Then we have the force of gravity acting on the mass. We're going to assume that the weight of the spring is negligible, that it has no mass effectively. We're just going to focus on modeling the mass only of the object. That's at the end of the spring. Then springs can have a damping force. A damping force is a force that acts counter to the velocity, much like air resistance might act in a situation where an object is thrown through the air or through some other medium. And the damping force is what's going to cause the oscillations, the amplitude, to decrease over time. And then there's potentially external forces, something else that's driving the motion of this mass. So symbolically, we have the force as a function of time is a function of what's composed of these four components: the spring resistance force, the force of gravity, the damping force, and a potential external force. Now, Newton's law says that the total force is mass times acceleration. The force due to spring resistance is going to be a constant times x and negative, because it's always acting in the direction opposite of x. So let's say that you're up here, then x is positive, and the spring is going to exert a negative force. It's going to try to push the object back down. It's going to exert a negative direction force. But if your object is below x equals 0, then the spring is trying to exert a positive force to bring it back to that location. So we have negative some constant times x is going to be our model for the spring resistance force. Now, the force of gravity is the mass of the object times the g, the gravitational constant. We're going to use effectively 9.8 whenever this surfaces in our work for G. And again, we have a negative because force of gravity is always down, and down we've established is the negative direction. Now, the damping force is a force that acts counter to the velocity of the mass. So its model is going to be minus some constant. This is a Greek letter mu, spelled mu, mu. It looks a lot like an M, which is unfortunate, but it's not the M, it's not the mass. It's another constant that has to be given or that we have to find, and it's a constant times the velocity. And because it's always counter the direction of the velocity, this term is also subtraction. And then we have our external force over here. And that could be any equation depending on what the external force is. Now these constants that we see here, let's say a little bit about them. The mass will always be positive. The K will always be positive. And of course the M and the G we're treating as a positive. The fact that gravity pulls down, that's why we have a subtraction there. So the G we're going to use as a positive G. The mu is also positive. So all of these constants are positive. And sometimes mu is going to be 0. And that would be a case where there is no damping. Now the units on all of these things. Every single one of these components needs to have a unit of a force unit. And in the metric system, we're only going to work in the metric system here, is the unit is newtons. So all of these have a newtons unit. Now mass has a unit of kilogram, and acceleration has a unit of meters per second squared. Let me write it this way. I'll put m colon and then put its unit. Mass is in kilograms, acceleration is in meters per second squared. Now when you multiply kilograms times meters per second squared, you get newtons. So a newton unit looks like this, kilogram meters per second squared. Now the K, the unit of the K is easiest to determine after we know what the unit of the X is going to be. Well, X is measured in meters. X is a length. It's a position relative to X equals 0. It's measured in meters, and therefore we want K to have a unit so that when I multiply K and X, we will get a unit of Newton. So the easiest way to do that is really just say that K is newtons per meter. So when I do newtons per meter times meters, I get newtons out of this. Now M, in this case here, I'm not going to write down what these ones are because G is meters per second squared and M is kilograms. So it's very similar to M times A. Let's look at the mu and the V. We want to determine what the unit on the mu will be, and it's easiest to first determine what the unit of velocity will be. The velocity will be in meters per second. And so mu needs to be a unit so that when you multiply mu and V, you get newtons. So effectively newtons divided by meters per second. Or you could write it this way, newtons seconds per meter. And this will be our damping coefficient. Okay, now if we take this equation and we factor out a negative k out of the first two terms, and I replace m with x double prime, because acceleration is the second derivative of position, and replace v with x prime, and now we can see our second order differential equation starting to emerge. Now I'm going to factor a negative k out of these first two terms, giving me this expression. Now I'm going to take this negative expression and this negative expression and add them to both sides, and so we wind up getting right here a second order differential equation. Now the next thing I want to do is a change of variable. I want to change from x being my variable to y being my variable, and we just have to determine what exactly y is relative to x. Well, this is our equilibrium. The green line here is our equilibrium. I'll put EQ here. That if the mass was just hanging there freely without motion, it would just hang at that length. And we're going to say that it's at a certain position, which we'll say is x naught. Now x naught is going to be a negative number because it's below x equals 0. So this line could also be described by x equals x naught. That's a funny looking 0 there. Let me make that look better. Okay, now if we take our force due to resistance from the spring, we know that that's equal to a negative kx. So when we're at the equilibrium, when y is 0, we know that at that position x equals x naught, that the force pulled down by gravity will be equal to the resistance force caused by the spring. Excuse me. And when those two forces are equal, that's why we have equilibrium. It's a perfect balance, and this object here will not be moving if it's on that green line and not being displaced. So these two forces will be equal, the gravity and the resistance due to the spring. So when I change x to x naught, I get the weight of, it has to equal the force caused by the weight of the mass, which is m times g, the mass of the spring times the gravitational constant. This tells us that x naught is equal to mg divided by k. Okay, we'll keep that in, negative k, I should say. Now, x naught will be negative because m and g are positive and so is k. So this represents a negative number. That's confirming we have a negative x naught because we're below x equals 0. Now, keep this in mind, that x naught is the same thing as mg divided by negative k. So over here, I could rewrite this differential equation, at least part right here, as x minus x naught. Now, what I'm going to do is do a transformation. I'm going to let y be equal to x minus x naught. Therefore, when x is changed to x naught, this becomes 0, equating y equals 0 and x equals x naught as the same location, which is what I want. Now, with this transformation, we know that y prime will just be x prime, because the x naught is a constant, it'll go away. And that y double prime will just be x double prime. So through this transformation, I can freely change x double prime to y double prime, which I've done. I can also freely change x prime to y prime, which I've done. And then the last component right here, let's make that blue to match. This transformation, x minus x naught, just becomes the y that we see. So our differential equation now becomes one that's in terms of y, where y equals 0 anyway, is our height that establishes our equilibrium, our mass spring equilibrium. And this is the differential equation that we are going to be working with. Now, a couple things to say about this. If there is no external force, then this will be 0. F of t will be 0, meaning this will produce a second order homogeneous differential equation with constant coefficients, because the m, the mu, and the k are all positive constants. And then if f of t, if there is a force, an external force acting on the system, then we would have to solve an inhomogeneous. Now, when f of t is 0, when this is a homogeneous differential equation, then what we say we have is free harmonic motion. And that's the purpose of this, or that's the subject of this topic. Topic 17 is on free harmonic motion. So we're going to have f of t be 0 for all the examples for this topic. The next topic we'll talk about what's called forced harmonic motion, where f of t will be non-zero. If there is no damping present, then the mu will be 0, and this term here will be gone. It won't be present. And of course, m is the mass, that will never be 0, and k is the, we're going to call this the stiffness of the spring. It's the constant related to the resistance force of the spring. So if k is larger, then we're going to have effectively a stiffer spring requiring more force to stretch at certain distances. And if k is small, then we have a weaker spring. So this k definitely or directly correlates with how strong or how weak the spring is. So it's referred to as the stiffness coefficient. So let's name these. Again, the m is the mass of the object, and it's going to be positive. The mu, we're going to call this the damping coefficient. Damping coefficient. And it's also going to be positive. And let's put units on all these. The mass has to be in kilograms. So if you're given a mass that's in grams, you're going to want to convert to kilograms first. The mu, its units, if we look back up here, that was the Newton seconds per meter. And then the K is called the, we'll call it the stiffness coefficient. And it's always going to be positive as well. And its unit will be, if you look back up here, the K add a unit of newtons per meter. All right, and then we're just going to pretty much be working with this differential equation right here to model this free harmonic motion moving forward. First example, a 2 kilogram mass is attached to a spring with a stiffness of 98 newtons per meter. So that's the M and the K are provided. The mass is pulled down 5 centimeters below spring mass equilibrium and then released from rest. Assume no damping or external forces are present. Find the model for the motion of the mass as a function of time and give the amplitude and period of the curve. Okay, so let's begin with our general differential equation right here that we're going to be using as our platform. We know that the mass is 2 kilograms. So we have 2y double prime, and make sure your mass is in kilograms. So if that was 2 grams, you'd have to do a conversion. Is attached to a spring with a stiffness of 98 newtons per meter. That's the correct unit. So this 98, we can use that for the K. So that's our K, and this 2 is our M. And we're assuming that there's no damping forces, so the mu is 0. So as soon as you see assume no damping, mu is going to be 0. So we wind up getting a differential equation that's simply 2y double prime plus 98y is equal to, and then no external force, so f of t is also 0. And this is what we want to solve. It's a simple second order with constant coefficients. I'm going to go ahead and divide everything by 2 to begin. So y double prime plus 49y is equal to 0. Find the characteristic polynomial next. Lambda squared plus 49 is 0, and then solve, and we get lambda is equal to plus or minus 7i. This gives us the general solution of y is equal to some constant times the cosine of 7t plus some constant times the sine of 7t. Now we have some initial conditions. The initial conditions are the mass is pulled down, let's read that second sentence, the mass is pulled down 5 centimeters. Now careful, that's in centimeters, so we're going to have to convert 5 centimeters to meters, because we want everything to be in terms of meters and kilograms and seconds for all these units to work in harmony. So the mass is pulled down 5 centimeters below spring mass equilibrium and then released from rest. So that means there's no initial velocity, but there is an initial position. And that y coordinate is going to be negative 5 centimeters because we're below spring mass equilibrium. Some of your homework might speak in terms of this in terms of left and right, by the way. When they talk about being right of equilibrium, you can think of that as being above. And left of equilibrium, you can think of that as being below. So just be mindful of that when you do the homework and you see left and right. So our initial conditions are going to be, we have y at time 0 is negative 5 centimeters. So that's going to be negative 0.05 meters. And y prime at time 0 is going to be 0 meters per second because it was released from rest, no initial velocity. Okay, now we got to find out what C1 and C2 are next. So let's do a derivative. Y prime, differentiate our general solution, and we get negative 7C1 sine 7t, and then plus 7C2 cosine 7t. And we're going to plug 0 in for t in both cases. And in the case of y, we should get negative 0.05 for the y. At the same time, t is 0. Well, cosine of 0 will be 1, sine of 0 will be 0, so C2 will be canceled, and we just get clean C1 is going to be negative 0.05. Now, plug into the second equation. Change y prime to 0. At the same time, you change the t's to 0. And this gives us negative 7, oops, no negative. Right, plug in 0. This part here will become 0. Sine of 0 is 0, so that's gone. Cosine of 0 is 1, so we just get 7c2. Which means that c2 has to be 0. So our solution winds up being simply y is equal to c1, which is negative 0.05 times the cosine of 7t. And here's our model. Now define the amplitude and the period. So if you might recall that when you have a sine or cosine and it's been stretched by a coefficient, that coefficient will reveal the amplitude. So we know that the amplitude will be 0.05 meters, and the period, if you recall from trig, when you have cosine or sine of a number times t, then the period will be the 2 pi divided by that coefficient, so divided by 7. And keep in mind that the period is a horizontal length, and the horizontal axis here is time, so this would be in seconds. It's saying that every 2 pi sevenths seconds, the mass should be where it was before and repeat the harmonic motion. And the amplitude is going to stay 0.05. It will not change because there was no damping. Now, I've gone ahead already. Let me go ahead and circle these as part of my answer. I've gone ahead already and typed some of these functions into Desmos here, but let me open that file. Okay, and there are several functions here that I've already graphed. These are all going to be relevant to today's lecture, and the top one is the one I'm going to reveal first. So y equals negative 0.05 cosine 7t, and I'm only going to graph it for t being positive. And here is a model of our harmonic motion. If you were to click any two of these numbers, notice that to go from one peak to another peak, that horizontal length, which is a time length, is our period. So to go from pi sevenths to 3 pi sevenths, we've increased by 2 pi sevenths. So our period is 2 pi sevenths. That's revealed here by comparing peak to peak. You can also see the amplitude is 0.05. And because there's no damping, the amplitude never changes. This spring will just go back and forth to the same amplitude forever. The harmonic motion will not diminish over time. Now that this, of course, is not realistic. Springs always have damping forces. But if there was no damping force, this is what you would expect. Or maybe a spring isn't involved. Maybe this is some other phenomenon and there perhaps is no damping force and we expect a forever oscillation. Okay, let's go to the next slide here. Before we go too much further, we need to do a little bit of a trig review because some of our solutions are going to have mixtures of sine and cosine. Right, that wasn't the case up here because C2 turned out to be 0, getting rid of the sine component. But that's not always the case. Sometimes our solution will have cosine and sine both. And so what we want to do is, if that's the case, can we determine the new amplitude and the new period? So the way to do that is to use some trig identities to convert this expression that has both sine and cosine. Notice they have the same argument, both 2x, and to express it in terms of cosine only in this way, where there's a new amplitude A, and then this B it's going to be contribute to a phase shift. But the period will still be to find the period, you'll still do 2 pi and divide it by the coefficient of the x. So this is going to have a period of 2 pi divided by 2, a period of pi, but figuring out A is important for determining the new amplitude. Now the way we're going to do this is to use a trig identity on the right side, the cosine of a difference. And the cosine of a difference, the A is going to be present still, so I'll just use the identity on this. The cosine of a difference is the cosine of the first, so cosine of 2x, times the cosine of the second, and then plus, and then the A will distribute, and then we do sine of the first, sine of the second. Okay, so let me move this over again just slightly more. So this is what we get when we do the cosine of alpha minus beta formula, cosine subtraction identity. Now what we want to do is equate on both sides of this equation, and I'm going to use color coding to do this, the coefficients. So this 5 has to be equal to A times cosine B, because those together form the coefficient of cosine 2x. And this negative 3, which is the coefficient of sine 2x, has to be the A times the sine B, because those form the coefficient of sine 2x. So this gives me a sequence, or a system of equations. Here's the first one. 5 has to be A cosine B. And the other one is that negative 3, don't mind the subtraction, has to be equal to A sine B. We'll put these together and I'm going to create a reference triangle here, where the cosine of B is 5 over A, and the sine of B is negative 3 over A. And we're going to assume A is positive. we can do this in such a way that a will always be positive. So if a is positive, then I know cosine of b is going to be therefore a positive number, and the sine of b is going to be a negative number. that happens in the fourth quadrant. Excuse me, where the cosine is positive, but the sine is negative. So I'm going to draw a picture of a triangle in the fourth quadrant. There we are. And we know that the b is the angle, the fourth quadrant angle. And the cosine of b is 5 over a. So 5 will be this adjacent, and a will be our hypotenuse. And the sine of b will be negative 3 over a. So you can see, like, this would be the origin, and this point here would be, in fact, in the fourth quadrant, right 5 down 3. And from this triangle, we're going to use this to construct a and b. So a is simply going to be the Pythagorean theorem. We'll do the square root of negative 3 squared plus 5 squared. So a is going to give us 9 plus 25. We're going to get radical 34 will be a. And b will be the arc tangent of negative 3 over 5. Now sometimes you have to adjust the arc tangent to make sure you're in the correct quadrant. We're looking for an angle that's already in quadrant 4. And if you recall, when you arc tangent a number, you're guaranteed to get an angle that's between negative 90 degrees and positive 90 degrees. In other words, a fourth quadrant and first quadrant answer. Something that exists somewhere in this window. So if you need to actually get an angle over here, you're going to have to adjust this arc tangent by adding pi to it to get it to the correct quadrant. We'll see that happen in the next example. But here we don't need to do that because this is in quadrant 4 already. And that's where we want our angle to be. Okay, so we can rewrite the sine cosine expression in terms of only a cosine. So we get that a, which is radical 34, times the cosine of 2x minus b, and b is the arctangent of negative 3/5. It really doesn't matter what that b is, and I'm just going to put a b there because it doesn't affect the period or the amplitude. So the amplitude will be the coefficient of the cosine, radical 34, and the period will still be the 2 pi divided by the coefficient of x, so divide by 2. We'll get pi as the period in this case. So when your answer is a combination of sine and cosine, you can really just take the coefficients of negative 3 of the sine and cosine, which is 5 and negative 3, and then do Pythagorean theorem with them and get a hypotenuse, and that's going to be your new amplitude. And your period is going to be what you'd have done before. Just each of these arguments is a 2x, so take 2 pi divided by 2, and you'll get your new period. We're going to use those shortcuts on this next one. But I should also say, maybe I'll do a little bit more in this next one than I would have done before. The coefficient of the cosine you can think of as an x-coordinate, and the coefficient of sine as a y-coordinate when you make your reference triangle. So I am skipping some of the things. I'm not redoing all this. I'm going to go straight to this reference triangle. And the coefficient of cosine is negative 1, so we're going to go left 1 and then up 2. And the beta, remember this is the origin, so that the b, not the beta, but the b is this angle right here. So the amplitude is going to still be, and the a is the hypotenuse still. So the amplitude is still going to be the Pythagorean theorem, which is square root of negative 1 squared plus 2 squared. That's going to give me a radical 5. That's going to be our amplitude. And the b will be an arctangent of opposite over adjacent, so 2 over negative 1. But when you do an arctangent of a negative, you're going to get a fourth quadrant answer. So to make sure that you get this into the second quadrant, which is where our picture is, then you're going to have to do the adding the pi. So when you do your arctangent, you're always going to have to make sure you add the pi if you're looking for an angle that's in the second or third quadrant. If your angle is in the first or fourth quadrant, then you don't need to add the pi because arctangent already gives you an angle that's in the first or fourth quadrant. Now, of course, finding b is not necessary for giving the amplitude and the period of this combination of sine and cosine. That's why I hesitated at first and thought, well, maybe I'm not going to bother finding b in the first place. But I did want to show you how to truly make this conversion to this statement here and to find the accurate choice of b, you're going to have to know sometimes you have to add pi to your b to get the angle that you're after. Anyway, so we can rewrite this as radical 5 times the cosine of 3x minus b, whatever b is. And the amplitude of this will be the radical 5. And the period will be the 2 pi divided by the coefficient of x, which is divided by 3. So 2 pi thirds will be the period. Okay, now let's go on to another example. So this example here is effectively the same as 2 slides before. I haven't changed anything except one bit of information, this part right here, where on slide 2 we released the mass from rest, but on slide 4 we're going to give the mass an initial downward speed of 0.2 meters per second. Everything else about this scenario is the same. Okay, so our mass is 2, so we have 2 y double prime. Our mu, there's no damping still, so we have 0 times y prime. The stiffness coefficient of the spring is the 98 still, so plus 98y. And we're still assuming no external force, so equals 0. And this will lead us to the same general solution that we had before. So I'm just going to go straight to that. Y of t is equal to c1 cosine of 7t plus c2 sine of 7t. The only thing that's going to be different is that our initial conditions are now different. Y of 0 is still negative 0.05 meters, but y prime of 0 is now no longer 0. That's the only difference here. So given a downward initial speed of 0.2 meters per second, so that means our y prime is going to be negative 0.2 meters per second. Be mindful of that direction. Downward velocities are negative, upward velocities are positive. Okay, and y prime, in fact, let me just go back up here and copy this. Y prime is the same as it was before. And now we can plug in 0 for t. Let's do the first equation. Plug in 0 for t and change y to negative 0.5. So negative 0.05, sorry, is y. And when t is 0, we just get c1 again. So c1 is still negative 0.05. But now when I plug in y prime equals negative 0.2 at the same time that I plug in 0 in for t in this derivative equation, and we're going to get 7c2 on the other side. So c2 is negative 0.2 over 7. Well, 0.2 is 1/5, and divide 1/5 by 7, we get negative 1/35. So our solution to this then will be y is equal to c1, which is negative 0.05 times the cosine of 7t, and then minus 1/35 sine of 7t. And our amplitude. The amplitude of this wave, notice this does have a mixture of sine and cosine, same argument, 7t and 7t, so we can just do the Pythagorean theorem with the coefficients. And when I do that, so we're going to have the square root of, let me move this over slightly, zoom in. The amplitude is going to be the square root of 0.05, that's negative technically, but the square will get rid of that, plus, and then negative 1/35 square root, and I already did the calculation ahead of time, and then so to save time I'll just put the result here. It's 0.0576. And the period is going to be found by taking 2 pi and dividing it by the coefficient of the t's, so dividing by the 7. And this will be our new period. That one I did not convert to a decimal. But let's take a look at a graph of our solution now and see how it compares to the other one. Now I've already typed it all in. It's the second line. So I'm going to reveal it and we can see both at the same time. If I click on the blue and find 2 different peaks, those peaks should be, this blue curve should have the same period as the red curve. So the distance between peaks should still be 2 pi sevenths and measured in seconds. But the blue wave has a different amplitude. Notice how high up these peaks are relative to y equals 0. So we have a new amplitude but the same period. And if you look at initially what's going, oops, that's not what I wanted to do. I want to just zoom in right here. You can see the red motion started from rest. So the tangent line was 0. on the red curve. But the blue curve started with a downward speed before it was brought back up. And that caused it to have a slightly different amplitude. And because there's no damping, the peak that it achieves, the blue curve peak down here, that's going to wind up being the amplitude for the entire blue curve because no damping is happening. Okay, let's go back to our notes and look at the next one. We're going to introduce damping now. So this new example, the initial conditions are now all the same. The only thing I'm changing now is this line right here. We assumed no damping or external forces. Now we're going to assume still no external force, but the motion has a damping constant now of 4 Newton seconds per meter. So that's going to be the mu. So the mass is still 2. We're not changing that. So 2y double prime. We now have a damping coefficient of 4 times y prime, and then the stiffness coefficient still 98 times y, and still no external force. So this one's going to have a different solution. We need to write the characteristic, or first I'm going to divide everything by 2. We'll make the numbers a little bit easier to work with. So we have 2y prime plus 49y. Characteristic equation is lambda squared plus 2 lambda plus 49 is equal to 0. And when you solve this one for lambda, you have to use the quadratic formula here. And we wind up getting -1 plus or minus 4i radical 3. I did this ahead of time to save time. That means that our general solution, y of t, is equal to some constant times e to the negative t times the cosine of 4 radical 3t and then plus some constant times e to the negative t times sine of 4 radical 3t. Now to save time, I've already gone ahead and worked out the initial conditions to get what C1 and C2 are. And you can confirm this by using Wolfram alpha or something else to solve these differential equations really fast. But we know that y of 0 is -0.05 meters, and y prime of 0 is still the -0.2 meters per second. And when you solve for C1 and C2, we wind up getting that C1 is it's still -0.05, and C2 will wind up being -1/16 radical 3. Therefore, our particular solution, let me copy and paste this, replace the C1 and the C2 with their values. C1 is -0.05, and C2, let's make this subtraction, -1/16 radical 3 e to the negative t times sine 4 rad 3t. Now, if you like, you could factor out the e part. Let me make this look a little bit better over here. -0.05. You could factor out the e to the negative t. No need to do that, though. And also notice that we are not asking for the period or amplitude. The reason is because there's damping now, and the damping is going to cause the amplitude to change, although the period will should remain consistent. We should get a period of 2 pi divided by this 4 radical 3, but the amplitude is going to be changing. Let's reveal this solution. I've already typed it in, and we get this green. Let me hide the blue and the red so that we can just look at the green. And this represents the motion of our mass with the particular damping coefficient. If I reveal the blue and zoom into where it got started, you can see that they have the same initial trajectory, but that because the green is being dampened, it didn't make it as far down as the blue did. And you'll notice the period, though, is the same. The peaks and valleys correspond to the same times. It's just that the amplitude is changing as we go forward. So one question you could ask in a situation like this is, what's the max displacement from equilibrium? And you could easily find that by finding the highest or lowest peak. So the furthest that this mass ever gets from its mass spring equilibrium is 0.05693 meters below. None of the other peaks are further from the horizontal axis here. That's our furthest one. So we'll call that the max displacement. Okay, next one. A 2 kilogram mass is attached to a spring. So the only thing we're going to change here now is we're going to increase the damping constant. See what happens, what effect that has. Everything else is going to be the same. We're just going to keep pushing that damping constant to higher and higher numbers. And so in this case, we have 2y double prime. The damping constant has been increased to 28, so plus 28y prime. And then ky. The k is 98 times y. And 0 is our external force. Again, divide everything by 2 to begin. Now I'm going to convert to a characteristic polynomial. Lambda squared plus 14 lambda plus 49 is equal to 0. And this one actually factors. It factors into two equal factors. It's a perfect square. So we get lambda equals -7, and we get it twice. And when that happens, our general solution, our y of t is going to be some constant, c1, times e to the lambda t, so -7t, and then plus c2 times t e to the lambda t. So we get that extra t in there. And then, again, just to save time, I do a derivative, I do y prime, and then I plug in our initial conditions. Our initial conditions are still the same. Keep in mind you're going to have to do the product rule in this part here when you do a derivative. That was true up here as well. You had to do a few product rules here and there both. And I'm skipping that work just for time's sake. We know that if y of 0 is equal to -0.05 meters, and y prime of 0 is still -0.2 meters per second, that this gives me that c1 will wind up being -0.05, that's still the same. c2 winds up being -0.55. Feel free to pause the video and do that work to confirm that you get this or not. So then our solution go ahead and erase these constants. Drag this over slightly. So C1 is going to be -0.05 and C2 is -0.55. And I don't ask for a period or amplitude for this case either. Notice we don't even have sines and cosines anymore in our solution. That's interesting. Let's see what this looks like when graphed. Hide the green and put the new one in. This one has so much damping that the object never goes past, it never goes higher than the equilibrium. It just shrinks right back to equilibrium. It returns right back to equilibrium, effectively. And then hangs out at equilibrium. This is a case where we say that the system is critically damped. Remember that word, we'll talk about it again in a moment. So critically damped. It does not allow any oscillation. And the next one is, we go a little bit higher with the damping constant. Everything else is the same. So we have 2y double prime. This time mu has been increased to 32, so 32y prime. And the k is 98 times y equals 0. Divide everything by 2 to begin. Let's make things a little bit easier. Characteristic polynomials, lambda squared plus 16 lambda plus 49 is equal to 0. Quadratic formula is needed on this one as well. And we get lambda is equal to -8 plus or minus radical 15, which when you decimalize these, you get about -11.873 and -4.127. So we get two different negative lambdas. Now I'm going to go straight to the solution. And I used Wolfram alpha to get there. But these are both real numbers. And so let me write down the general. The general solution would be some constant times e to the lambda t, so negative 8 plus rad 15 t plus some constant times e to the other lambda t, so negative 8 minus rad 15 t. And those expressions are both negative, so it's e to a negative number t and then e to a negative number t. And with Wolfram, we have the same initial conditions as we had before. Right, so y of 0 is equal to negative 0.05 meters, and y prime of 0 is negative 0.2 meters per second. And we wind up getting the following as a particular solution. Y of t is equal to, and I'm going to do approximate because I did some rounding of the coefficients. It's about 0.0524597. I did reveal a bunch of them. E to the first one, so negative. Well, actually, this coefficient actually is the coefficient of, it's the C2, so it's actually that one there. Just want to make sure that that's clear. Negative 8 minus rad 15 t, and then minus 0.10246 times e to the other lambda t, which is negative 8 plus rad 15. Let me move this stuff around so I can write this all in one line instead. And let's go ahead and graph it and see what this looks like. This is the final graph here, the one in black. Notice it also appears to damp, and it dampens so much that it just returns back to equilibrium. Now look at these 4 solutions here, all of them that had the same initial conditions. The first one did not have the same initial conditions, if you recall, the red one, because that one was released from rest. But the last 4 examples we did all had the same initial conditions. And of them, notice that the blue was the one that had no damping, so it managed to get the furthest down. The green had some damping, the purple had more damping, and the black had the most damping. Now, in the case of the black, we say that the system was overly dampened. Now I want to just explore the cases that are when we get no damping, over damping, critical damping, and just regular damping, but not over or critical. Your characteristic polynomial is going to be where we're going to look at, because your characteristic polynomial is always going to be of the form m lambda squared plus mu lambda plus k is equal to 0, where m, mu, and k, and mu could potentially be 0. I'm going to graph this as a polynomial. Let's hide all these things and type in y equals, I'll use m, m x squared plus, I'm going to use b instead of mu because the Greek letter isn't here, so I'll say bx, and then plus k. And I'll add sliders for all of them. Now keep in mind that m can't go any lower than, it has to be positive, but I'm going to put a lower limit of 0 on that. And let's put a max of 5 on there. B, the lowest B can get, that's the damping coefficient. That can go as low as 0. And again, we'll put a max of 5 on that. And K is the stiffness coefficient, and that has to be positive as well. So let's say 0 to 5. And I just want to show you the different kinds of graphs, possible graphs we get as these values vary. They're always going to be parabolas. In fact, let's pause some of these and just toy with one of them. So the m is the leading coefficient. Adjusting that seems to only have the, well, it seems to widen. If m is large and we get a narrow parabola, if m is small, getting close to 0, we get wider parabolas. K is just vertical shifts. That makes sense. That only affects vertical shifts. And then the B, looks like the shape doesn't change, but the vertex location changes. And B could be 0. If B is 0, then notice we're going to get parabolas that are opening up somewhere on the positive x-axis. And all these parabolas don't have any intercepts. It's going to have two imaginary roots. Your roots are going to be plus or minus the radical of k times and then times I. So in this case here, when b is 0, when the damping coefficient is 0, your characteristic polynomial is just a parabola whose vertex is on the positive y-axis. This is the case where we have a sine wave or a cosine wave as an answer. No diminishing amplitude. Once we introduce damping, however, the vertex will shift off of the y-axis. And so either we're going to get a parabola like this, if b is dragged up to such a point. In fact, why don't we just make m be 2, because our mass was 2 in our problems. I'll just type it in 2. Let's say our mass is 2, and the k was 98. I have to do some zooming out to see these things. Okay. And the b, when there was no damping, we just had a 0, and we had a parabola vertex on the positive y-axis. And then as b increases, let's allow b to get as large as 40, and I can use the slider. Notice what happens. Our parabola just moves and moves. So if b is something like this, notice that the parabola has a vertex in the second quadrant, and so the two roots of the characteristic polynomial are still both imaginary, but now they're going to have a real component. When b was 0, we had imaginary roots with a non-real component. Now all of these ones are going to have imaginary roots with a 0 component. Widen that slightly. And when b got to, if you recall what b had to be, so that we had one root exactly, it was that b was 28. That's when the characteristic polynomial hits the x-axis, finally hit the vertex on the x-axis, and we get one real root repeated. That was the -7 repeated twice. But once we go higher, and this was the critically damped scenario. So b is 0 is no damping. All b's between 0 and 28 are going to be various levels of damping, but not critical yet. When b gets to 28, this is the one choice of b where we're going to have a critical dampening. And then once b goes more than that, notice we get two negative roots to our characteristic polynomial, and they're both real. So we're going to have an e to a negative t plus an e to a negative something times t. And this is the overly damped. Oops, we'll keep that at 98. So anything more than 28 gives us two negative real roots. 28 itself gives us one real root, negative, repeated. Between 28 and 0 gives us two complex roots with a real component. And then b equals 0 gives us two imaginary roots, no real component. And if you look at our work here, you can see that happening. Let's go back to right here. This is when b was 0. We had no damping. We had two imaginary roots, no real component, right? There's no a here. It's just plus or minus bi. That gives me a sine and cosine combined, which means that the ultimate answer could be expressed in terms of just cosine. So we're going to have a sinusoidal wave. And that was still true even when I had a different initial condition. Right? We got this sinusoidal wave. However, when we had a b that was between 0 and 28, we wound up with two imaginary roots, but with a real component. So there was an e to the negative t involved in each, meaning that these are each going to shrink to 0 as time goes on to infinity. So we're getting damping this time. But it wasn't critical or overly damping. So we still had a harmonic motion oscillating around the axis of equilibrium. And then when the mu became 28, we had the critical damping, where we had the vertex of the characteristic polynomial finally hit the negative x-axis, giving me two identical real negative roots, giving me only exponentials and part polynomial as my solution. And this was critical damping, happened at 28. And then once the mu went higher than 28, like to 32 and higher, we wound up getting multiple negative real roots, hence e to a negative plus e to a negative, and we had the overly damping. Okay, and this wraps up our discussion on free harmonic motion. Next topic, we're going to be doing forced harmonic motion, which is where the forcing function over here will be non-zero.